quick. So we're going to look at solving simultaneous equations using matrix methods. Just to remind you of last lesson, we've finished all the inverse and determinants, and we just talked about this using matrices to solve simultaneous equations. We did it there. We talked about the fact you might have no solutions, one solution, infinitely many solutions, and I also showed you an anecdote using pieces of paper, which maybe worked, maybe didn't, who knows, for three-dimensional situations. Now we're going to go through the process. So here is procedurally how we can solve a simultaneous equation. If you're reading widely beyond the textbook, you might find something called the Gauss-Jordan method or the Gauss method for solving simultaneous equations. It's a really nice procedural method that works really well, but it's not actually covered in the content now. So you don't need to know about that. All you need to know is how to do it using inverses. So if you want to solve simultaneous equations and they're set up like this, where our coefficients of x and y are a, b, c and d, and the solutions to those equations, S1 and S2, we write this out as a matrix equation. So you can actually break this down to be a coefficient matrix multiplied by the variable vector, so it's a variable column vector, x, y, and it equals a solution vector, column vector again, or column matrix again, S1, S2. And so we've got A and S, and we've also got our variable vector, which is sometimes called x. So you might also see this as AX equals S. Now remember, we know S, we know the solutions, we know the coefficients, we just don't know x and y. That's what we're trying to find. So if we can rearrange this, we can find x and y. And the thing is, you now know how to do that, and you know how to do it with technology as well, which could help you, but you know how to do it technically using inverses. So if I've got some coefficient, square matrix with coefficients, a, b, c and d, multiplied by x, y equals the solutions. If I can find A inverse, then I can do this situation here. I can solve this equation. I do a left multiplication by the inverse, and that eliminates the A, giving me the identity. And on the other side, I have to do a left multiplication by the inverse again. So you notice it's A inverse S, not SA inverse. And by the way, SA inverse wouldn't work anyway because A inverse would be a 2 by 2 and S is a 2 by 1 and the dimensions wouldn't match. When you do that though, a 2 by 2 multiplied by a 2 by 1 will leave us with a 2 by 1, and that will match the dimensions of x, y, and it will just give us x and y. The numbers that are in the 2 by 1 will be x and y, and you've solved your matrix. So I'm going to show you how this works for this blue one here, and you'll see it in action. So I'm going to start by defining my A. A is equal to 4, -1, 2 and 3. And S is equal to 27, 17. And of course I've got X and Y. Be a little bit careful. I'm not going to try and trick you into the examination material, but I can't say anything about the external exam. Be careful that your X and Y are in the same order. It will come up probably in the textbook at some point that the second equation has x and y swapped, and it's a really common way of sort of tripping you up. So just be careful with that. Now, I've got A, it's gone. That's not working. There we go. I've got AX, oh that's not working well. This is all stalled on me. So, go back to the first one, that's still gone. Okay, AX equals S, and I'm going to show that A inverse AX is equal to A inverse S, and therefore X will be equal to A inverse S. You do need to still show these steps each time you do a question like this, but it's fairly trivial. So all I need to do is determine A inverse multiplied by S, and I'll have my solutions, max.
Do we always need to show that A inverse times A becomes the identity?
You should.
Or can we just cross it both out?
You probably, look, again, I'd be happy if you wrote that. You have to have something here to tell me what you've done. Don't just go straight from there to there.
Yeah.
But I don't know whether there's going to be marks allocated for that in external exam, so I would just do it. So really, we write I here, and then we can write X equals the end result of that. So I'm going to determine my A inverse. A inverse is equal to 1 over the determinant, which is AD minus BC. Tell me if I get this wrong. D, negative B, negative C, A. Is that right? And in this case, I've got, so I shouldn't have zoomed out there, 4, negative 1, 2 and 3. So the determinant of A, I might just work out on the side here, is equal to 4 times 3 minus negative 1 times 2, which is 14. So I get 1 over 14 times by D, which is 3, negative B is 1, negative C is negative 2, and that's 4. And so my inverse is 3 over 14 times, in fact, what I'm going to do is I'm going to leave it like this. I might leave it in that form. I've taken that scalar out, taken that fraction out. It's actually going to make my multiplication by S a bit easier. So I get this then. Or actually I might just write X, because I've shown that step. X equals 1 over 14, which I will have to incorporate in a bit later. 3, 1, negative 2, 4, times by the solution matrix, which was 27, 17. And so I do 3, 1 times 27, 17. 3 times 27, that's 1 over 14, times by 81 plus 17. And negative 2 times 27 is negative 54. 4 times 17 is 68. So it's negative 54 plus 68. That gives me 1 over 14 times by 98, 14. And 98 is some whole number. Is it 7 times? I think that's 7, 1, but you want to check there. Therefore, X equals 7 and Y equals 1. Does that make sense? So X is XY. Now I know you'll be thinking, well, again, that realistically probably took longer than solving it pen on paper, using the method you know. But that's a small scale question. One, it works out with a nice whole set of numbers, which will come out easier. If that was a decimal, or worse yet, irrational in some way, this will procedurally be easier to do. You won't be dealing with harder numbers. And secondly, if it was a 3 by 3, so 3 equations, 3 variables, or 4 by 4, and you can rely on technology, this will do that stuff for you. Okay? Max.
Well, the inverse, if you have A times A inverse, is that the same as A inverse times A?
It is, but the problem here is that to do A times A inverse, you've got to try and slot that A inverse in the middle.
Yeah.
So if you multiply this by A inverse on the right-hand side, it would go on the other side of X.
Oh, yeah.
And X being a 2 by 1 can't be multiplied by 2 by 2. So you've got to be a bit careful you get the left-hand side, right-hand side multiplication right. But this is, if you get a question like this in your exam, you're writing that down, like literally bit for bit, because that's exactly how your simultaneous equation will be set up. So you'll start there, you'll get to there, that you're just writing that down. Just know that and practice it. Bam, there we go. Sorry. Example 3 and example 4. I'm going to put those up there and give you a bit of time to try that process with example 3. But this time the solution matrix will be A, B instead of X, Y. Otherwise it's the same. So I've just given everybody a go at this question, and there's a solution. And I've sort of suggested about 5 minutes would be appropriate for this, particularly after you've practiced a bit. Are there any questions on this one? So I'd like to do example 4, then I'm going to leave you alone for a little while, maybe even for the rest of the lesson. So in example 4, this is a slightly different take on it, and it's a bit of an investigation. Hopefully it will develop your understanding of the situation a bit more. But I'd like you to try and develop an example that generates an A that is not invertible. And what does this mean? So we'll do this together, but I'm suggesting I want to go A times X equals some solution matrix. And I just want to develop an A that's not invertible. Can anybody suggest a 2 by 2 A that is not invertible?
6, 4, 3, 2.
6, 4, 3, 2. Does anybody want to support that or disagree with it?
No, he's right.
Right, okay, so it seems like you guys are cotton on pretty quick to the fact that the determinant has to be 0 for it to be not invertible, and the determinant here is 6 times 2 minus 4 times 3, which is 0. So this is not invertible. Now, if I put into here, what solutions do you want? 11 and 12. So this matrix with a non-invertible A, which means we can't solve it using inverses, would come out with this system of simultaneous equations that looks like this. 6x plus 4y is equal to 11, and 3x plus 2y is equal to 12. What does this mean? What does it mean, the fact that it's not an invertible matrix for the coefficients and we can't get an answer using that method? What does it mean for this system? Can you solve that?
Yes.
Okay. Solve it.
Coefficients are bigger. Find x and find y.
What if one of them's, what if there's negative coefficients in there?
It doesn't say negative.
But how are you going to get a...
You have someone who's
So Harvey's made a pretty good point. How does this one equal 12 if the coefficients here are smaller? And I do want to just point out that does sometimes happen, not quite like this, but it does sometimes happen if you've got negative x's and y's. But also this wouldn't work if that was 7. If that was actually equal to 7, it still wouldn't work. If that was equal to 5, it still wouldn't work. If it was equal to negative 10, it still wouldn't work. So there's a bit more depth to why it's not working. Any takers? So?
They're parallel.
They're parallel.
What?
Because if you times the bottom one by 2, it's just equal to...
Let's look at it like that then. Let's do that. Okay. So if I multiply the bottom one by 2, I now get this new equation, which is 6x plus 4y equals 24. And in terms, you go back to our proof stuff, what's this called now? 6x plus 4y equals 11, and 6x plus 4y equals 24. This is a contradiction. So we've got a contradiction. And in fact, the conditions required to make this non-invertible, those two must multiply to get the same value as those two. And any way you do that, you'll end up with this being just a scalar multiple of that. And even if I said, okay, because you might say, oh no, we can fix this. What if we made this, in the original equation, what if we just made that 24? Then it would work, wouldn't it? But then, and this is what I like about what you just said a second ago, Dylan, if you drew these two lines, I'm not going to go into the details, but if you drew them, the original one we had looked like this. We had the top one, and then we had a second one, and they were parallel and didn't touch. If I change it, we get a third one, so this one here now becomes exactly like the second one. They're parallel and on top of each other. There's an infinite. So in the original situation, there were no solutions because they were parallel and didn't touch. In this new situation, this one-off case where it actually does seem to work, you can't solve for x and y because, for example, x could be 2 and y could be 3, and that would work. Or x could be 10 and y could be negative 9, and that would work. So there's lots of different situations. There's an infinite number of answers, ultimately. So that's the two problems. I mean, remember, if we go back to what we did last lesson, we said there's either an infinite number of solutions, no solutions, or one solution. Most of the time, for two variables, there's one solution, but not always. So just be careful of that. Look for that contradiction, and it will only appear if you've got a non-invertible coefficient matrix. So if you get a non-invertible coefficient matrix, that's the problem. And you can make that comment. If you get an invertible coefficient matrix, you have one solution and you can find it pretty easily. Any questions?